Welcome to this comprehensive guide on the identity rule for limits. This fundamental concept serves as a crucial building block in calculus, and understanding it will help you master more complex limit laws. Before we dive into the identity rule, let's quickly review what a limit is. A limit describes the behavior of a function as its input approaches a specific value. It tells us what value the function is getting closer and closer to. The identity rule states that for any real number a, the limit of x as x approaches a is simply a itself. Mathematically, we write this as the limit as x approaches a of x equals a. This rule might seem simple, but it's incredibly important. First, it serves as the foundation for all other limit laws. Second, it helps us understand how functions behave near specific points. And third, it's essential for advanced calculus concepts like derivatives and integrals. Here's a simple visual example. Consider the function f(x) equals x, shown as this yellow line. When x approaches the value 3, the function value also approaches 3. This demonstrates the identity rule in action. The limit equals the value we're approaching. In the following sections, we'll explore this concept in much greater detail, see how it connects to other limit laws, and work through several examples to solidify your understanding. To truly understand the identity rule for limits, we first need to explore the foundation it's built upon, the identity function itself. The identity function is beautifully simple. It's defined as f of x equals x. This means that whatever value you input for x, the function returns that exact same value as its output. Let me show you some examples. If x equals 2, then f of 2 equals 2. If x equals -3, then f of -3 equals -3. If x equals 5.7, then f of 5.7 equals 5.7. The output is always identical to the input. Now let's visualize this function graphically. When we plot the identity function on a coordinate plane, we get a very distinctive and important graph. The graph of f of x equals x is a straight line that passes through the origin and has a slope of exactly 1. This line extends infinitely in both directions, always maintaining the property that the y-coordinate equals the x-coordinate. Notice these key points on the line. At -2, the coordinates are equal. At the origin, both coordinates are 0. At 1, 1, again they're equal. At 3, 3, the pattern continues. Every point on this line has the property that its x-coordinate equals its y-coordinate. Watch this red point as it moves along the identity function line. Notice how the x-coordinate and y-coordinate are always identical. As x changes, y changes by exactly the same amount, maintaining perfect equality. This direct relationship between input and output is exactly what makes the identity function so important for understanding limits. Imagine we want to find the limit of f of x as x approaches 2. As x gets closer and closer to 2, what happens to f of x? Since f of x equals x, as x approaches 2, f of x also approaches 2. The limit is simply 2. This fundamental property gives us the identity rule for limits. The limit of x as x approaches a equals a. This simple but powerful rule forms the foundation for understanding more complex limit laws. The identity function's direct input-output relationship makes it the perfect building block for understanding how limits work with more complex functions. Now that we understand the identity rule, we need to explore its close mathematical relative, the constant rule. These two rules work together as the fundamental building blocks for all limit calculations. The constant rule states that the limit of any constant c, as x approaches any value a, is simply c itself. This means constants are completely unaffected by what x is doing. To understand why this makes sense, imagine a constant function. No matter what x value we choose, the output is always the same constant value. Here we see the graph of f of x equals 3. Notice that no matter which x value we pick, the y value is always 3. This is the essence of a constant function. Our first example demonstrates the constant rule with a simple positive constant. We want to find the limit of 5 as x approaches 3. Since 5 is a constant, it doesn't depend on x at all. Whether x approaches 3 or 100 or -50, the value 5 remains unchanged. Therefore, the limit of 5 as x approaches 3 is simply 5. The constant rule tells us the answer immediately. Our second example uses a negative constant. We need to find the limit of -7 as x approaches -2. The constant rule works exactly the same way with negative constants. The value -7 is completely independent of what x is doing. Therefore, the limit of -7 as x approaches -2 is simply -7. The sign of the constant doesn't matter for this rule. Our third example shows that the constant rule applies to any constant, including mathematical constants like pi. We want to find the limit of pi as x approaches 1. Pi is approximately 3.14159, but regardless of its exact value, it's still a constant. It doesn't change based on what x is doing. Therefore, the limit of pi as x approaches 1 is simply pi. This demonstrates that the constant rule works with any type of constant, whether it's a simple number or a mathematical constant. Now we can see how the identity rule and constant rule work together. The identity rule handles variables, while the constant rule handles constants. Together, they form the foundation for evaluating all types of limits. Understanding both the identity rule and the constant rule is essential because they serve as the building blocks for more complex limit calculations. Every advanced limit technique ultimately relies on these fundamental principles. Remember this key insight: constants never change, regardless of what happens to x. This simple but powerful concept will help you recognize when to apply the constant rule in more complex limit problems. Now that we understand what the identity rule is, let's see it in action with our first example. This will be a straightforward application that demonstrates exactly how this rule works in practice. Here's our problem. Find the limit of x as x approaches 5. This is a perfect example for applying the identity rule directly. First, let's identify what type of limit this is. We have the function f of x equals x, and we want to find its limit as x approaches the value 5. Now let's recall the identity rule. The identity rule states that the limit of x as x approaches any value a is simply equal to a itself. In our specific case, a equals 5. So according to the identity rule, the limit of x as x approaches 5 should equal 5. Therefore, our final answer is 5. The limit of x as x approaches 5 is exactly 5. This demonstrates the power and simplicity of the identity rule. Let's think about why this works. The identity rule works because the function f of x equals x is continuous everywhere. As x gets closer and closer to 5, the function value gets closer and closer to 5, until at the limit, it equals exactly 5. This example shows how straightforward the identity rule can be. In our next example, we'll see how this rule combines with other limit laws to solve more complex problems. Now that we understand the identity rule, we need to see how it works together with other limit laws. The real power of limits comes from combining these rules to solve more complex problems. There are several fundamental limit laws that work perfectly with the identity rule. These laws allow us to break complex limits into simpler pieces that we can solve step by step. Here are the 4 key limit laws we'll use. The sum rule lets us split addition into separate limits. The product rule does the same for multiplication. The quotient rule handles division, and we already know the constant rule. The key insight is that limits preserve algebraic operations. This means we can break apart complex expressions and solve each piece using the appropriate rule. Let's start with a simple example. We want to find the limit of x plus 3 as x approaches 2. Here's our problem. We need to find the limit of the expression x plus 3 as x approaches 2. Step 1. We apply the sum rule. This allows us to split the limit of x plus 3 into the limit of x plus the limit of 3. Step 2. Now we apply our rules. The identity rule tells us that the limit of x as x approaches 2 equals 2. The constant rule tells us that the limit of 3 equals 3. Step 3. Finally, we simply add 2 plus 3 to get our answer of 5. This shows how the identity rule and constant rule work together through the sum rule. Now let's try a more complex example that involves both multiplication and division. We want to find the limit of 2x times the quantity x plus 1, all divided by 3, as x approaches 4. Here's our problem. This expression combines multiplication in the numerator and division by a constant. Step 1. We apply the quotient rule to separate the numerator and denominator into their own limits. Step 2. For the numerator, we use the product rule to split 2x times the quantity x plus 1 into separate limits. Step 3. Now we evaluate each piece. The limit of 2x as x approaches 4 is 8. The limit of x plus 1 as x approaches 4 is 5. The limit of 3 is 3. So we get 8 times 5 divided by 3, which equals 40 over 3. For our final example, let's tackle a more complex polynomial that requires multiple limit laws working together. We want to find the limit of x squared minus 2x plus 5 as x approaches 3. This polynomial involves powers, products, and sums. Step 1. We use the sum rule to break this into 3 separate limits: the limit of x squared minus the limit of 2x plus the limit of 5. Step 2. For x squared, we use the power rule. For 2x, we use the product rule to factor out the constant 2. The constant 5 stays as is. Step 3. Now we apply the identity rule. The limit of x as x approaches 3 is 3, so we get 3 squared minus 2 times 3 plus 5, which equals 9 minus 6 plus 5, giving us our final answer of 8. Notice how we used multiple limit laws together: the sum rule to break apart the polynomial, the power rule for the squared term, the product rule for the 2x term, and the identity rule to evaluate the limits. This systematic approach works for any polynomial. The key takeaway is that the identity rule doesn't work alone. It combines with other limit laws to help us solve complex limit problems by breaking them into manageable pieces. This systematic approach is the foundation of limit evaluation. Now we'll work through a more complex example involving a polynomial limit. This will show you how the identity rule works together with other limit laws to solve real calculus problems. Here's our polynomial limit problem. We want to find the limit of 2x squared minus 5x plus 1 as x approaches 3. First, we apply the sum and difference rule for limits. This rule allows us to split a polynomial into separate limits for each term. So our limit becomes the limit of 2x squared minus the limit of 5x plus the limit of 1. Now we'll evaluate each of these 3 limits separately using the product rule and identity rule. For the first term, we have the limit of 2x squared as x approaches 3. Using the product rule, we can factor out the constant 2. Then we apply the power rule to get 2 times the limit of x squared. The power rule tells us that the limit of x squared equals the limit of x all squared. Now we use the identity rule. The limit of x as x approaches 3 is simply 3. So we get 2 times 3 squared, which equals 2 times 9, giving us 18. Now let's evaluate the second term. For the second term, we have the limit of 5x as x approaches 3. Using the product rule, we factor out the constant 5, giving us 5 times the limit of x as x approaches 3. Again, by the identity rule, the limit of x as x approaches 3 is 3, so we get 5 times 3, which equals 15. Finally, let's evaluate the third term. The third term is simply the limit of the constant 1. By the constant rule, the limit of any constant is just that constant, so the limit of 1 is 1. Now we can combine all our results to find the final answer. We combine our 3 results, 18 minus 15 plus 1. Calculating step by step, 18 minus 15 equals 3, and 3 plus 1 equals 4. Therefore, our final answer is 4. This example demonstrates a crucial point. The identity rule is the foundation for evaluating polynomial limits. Every polynomial limit, no matter how complex, ultimately depends on the simple fact that the limit of x as x approaches a value is that value itself. This makes the identity rule one of the most important limit laws in calculus. Now that we understand the identity rule mathematically, let's explore how this fundamental concept applies to real-world situations in physics and economics. These applications demonstrate why the identity rule is so important in understanding dynamic systems and rates of change. In physics, one of the most important applications of the identity rule involves understanding instantaneous velocity. This concept bridges the gap between average velocity over a time interval and the exact velocity at a specific moment. Average velocity is calculated as the change in position divided by the change in time. This gives us the overall rate of motion over a time interval, but it doesn't tell us the exact velocity at any specific instant. Instantaneous velocity is found by taking the limit of average velocity as the time interval approaches 0. Notice how the identity rule is fundamental here. As delta t approaches 0, we're finding the exact rate of change at that moment. The limit process here relies on the identity rule. As delta t gets smaller and smaller, approaching 0, the ratio approaches the derivative, which gives us the instantaneous velocity. This application shows how the identity rule enables us to understand motion at the most fundamental level, connecting discrete measurements to continuous motion. In economics, the identity rule is crucial for marginal analysis. Marginal functions describe how economic quantities change with respect to small changes in production or consumption levels. Consider a total cost function where C of Q represents the total cost of producing Q units. This might include fixed costs of $100 plus $5 per unit, plus a quadratic term representing increasing marginal costs. Marginal cost is defined as the limit of the change in total cost divided by the change in quantity, as the change in quantity approaches 0. This gives us the instantaneous rate of change of cost with respect to quantity. Using the identity rule and other limit laws, this becomes the derivative of the cost function. For our example, the marginal cost equals 5 plus 0.2 times Q. This result tells us that for each additional unit produced, the cost increases by $5 plus 0.2 times the current production level. The identity rule makes this precise calculation possible. Similar analysis applies to marginal revenue and marginal profit functions, making the identity rule fundamental to economic optimization and decision-making. The identity rule is the foundation that makes derivatives possible. This connects our simple limit rule to calculus and enables analysis of rates of change across many fields, including physics, economics, and engineering. Every time we use derivatives to solve real-world problems, we're building on the foundation provided by the identity rule for limits. This demonstrates the profound connection between abstract mathematical concepts and practical applications. We've reached the end of our exploration of the identity rule for limits. This fundamental concept is truly the cornerstone of limit theory in calculus. Remember, the identity rule states that the limit of x as x approaches any value a is simply a itself. This elegant simplicity makes it the foundation upon which all other limit laws are built. Throughout this video, we've seen how the identity rule connects to the identity function, works alongside other limit laws, and applies to real-world problems in physics and economics. These connections demonstrate why mastering this rule is so crucial for your calculus success. Your journey with limits doesn't end here. I encourage you to continue practicing with polynomial limits, explore rational functions, and eventually move on to studying continuity and differentiability. Each concept builds upon the solid foundation you've established today. If you found this video helpful, please give it a thumbs up and subscribe for more calculus tutorials. I'd love to hear your questions or suggestions for future topics in the comments below. Remember, every expert was once a beginner, and with consistent practice, you'll master these concepts too. Thank you for joining me in this mathematical journey. Keep practicing, stay curious, and I'll see you in the next video, where we'll explore even more fascinating calculus concepts.